Chapter 1. Introduction to Cosmic Catastrophes. Welcome to Cosmic Catastrophes, a journey through the most dramatic and violent events in the universe. From the explosive death of stars to the powerful forces that shape galaxies, we will explore the phenomena that both create and destroy, shaping the cosmos as we know it. This chapter sets the stage for our exploration by defining what cosmic catastrophes are, why they are important, and how our understanding of these events has evolved over time. Cosmic catastrophes are astronomical events of immense scale and energy, often involving destruction or significant alteration of celestial bodies and structures. These events include supernovae, gamma-ray bursts, black hole collisions, and more, each having profound effects on their surroundings. The sheer magnitude of these phenomena challenges our comprehension and showcases the raw power of the universe. Understanding cosmic catastrophes is crucial for several reasons. Firstly, these events play a vital role in the evolution of the universe. For instance, supernovae not only signal the death of stars, but also seed the cosmos with heavy elements necessary for planet formation and life. Secondly, studying these phenomena helps scientists uncover the fundamental laws of physics, as extreme conditions provide natural laboratories for testing theories. Finally, recognizing potential threats from cosmic catastrophes, such as asteroid impacts or gamma-ray bursts, is essential for developing strategies to protect our planet. Throughout history, humans have observed and been fascinated by cosmic events. Ancient civilizations often interpreted these occurrences, like comets and supernovae, as omens or divine messages. For example, the supernova of 1054, which created the Crab Nebula, was recorded by Chinese astronomers and appeared as a guest star in the sky for weeks. The Renaissance period marked significant advancements in our understanding of the cosmos. The invention of the telescope by Galileo Galilei allowed for detailed observations of celestial bodies, revolutionizing astronomy. The subsequent discoveries of distant galaxies by Edwin Hubble in the early 20th century expanded our view of the universe and set the stage for modern astrophysics. Technological advancements have been pivotal in enhancing our knowledge of cosmic catastrophes. Modern telescopes, both ground-based and space-based, enable astronomers to observe the universe in various wavelengths, from visible light to gamma rays. Instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and the recently launched James Webb Space Telescope provide unprecedented views of distant and high-energy events. Moreover, particle detectors and gravitational wave observatories, such as LIGO and Virgo, have opened new windows into the universe, allowing scientists to detect and study phenomena like black hole mergers and neutron star collisions. These technologies have not only confirmed existing theories, but also uncovered new mysteries, driving the continuous evolution of astrophysical knowledge. To illustrate the impact and significance of cosmic catastrophes, we will explore several notable historical events. The 1572 supernova observed by Tycho Brahe challenged the prevailing notion of an unchanging universe. The Tunguska event of 1908, caused by a meteoroid explosion over Siberia, demonstrated the potential threat posed by near-Earth objects. Another critical event is the discovery of the first gamma-ray burst in 1967 by the Vela satellites, initially designed to detect nuclear explosions. This discovery opened an entirely new field of study in astrophysics, revealing the existence of extraordinarily energetic and distant cosmic explosions. As technology continues to advance, so too will our understanding of cosmic catastrophes. Future missions and observatories, such as the Vera-C, Rubin Observatory, and the Laser Interferometer Space Antenna, LISA, promise to provide even more detailed observations and insights into these phenomena. Additionally, international collaborations and data sharing will play crucial roles in enhancing our comprehension of cosmic events. The pursuit of knowledge about cosmic catastrophes not only satisfies human curiosity, but also prepares us for potential future challenges. By studying the most extreme events in the universe, we gain a deeper appreciation for the complexity and grandeur of the cosmos. This introduction has provided a foundation for our exploration of cosmic catastrophes. Each subsequent chapter will delve into specific types of catastrophic events, examining their causes, consequences, and the cutting-edge research aimed at understanding them. Join us as we embark on this journey through the most awe-inspiring and destructive phenomena in the universe. Chap Chapter 2: Supernovae, the explosive deaths of stars. Supernovae, the explosive deaths of stars, are among the most dramatic and impactful events in the cosmos. These colossal explosions outshine entire galaxies for brief moments, releasing immense amounts of energy and dispersing elements crucial for the formation of planets and life itself. Understanding supernovae is not only key to unraveling the life cycles of stars, but also to comprehending the fundamental processes that shape our universe. Stars, the fundamental building blocks of galaxies, undergo distinct evolutionary paths based on their initial masses. Low-mass stars, such as our Sun, spend billions of years converting hydrogen into helium through nuclear fusion. As they near the end of their lives, these stars swell into red giants, shedding their outer layers into space to form beautiful planetary nebulae. What remains is a dense core known as a white dwarf, which gradually cools over billions of years. In contrast, high-mass stars, those with masses greater than 8 times that of the Sun, follow a more dramatic and explosive path. These stars burn through their nuclear fuel at an accelerated pace, undergoing a series of fusion reactions that produce progressively heavier elements. Eventually, the core of such a star becomes dominated by iron, which marks a crucial point in its life cycle. The iron core of a massive star cannot generate energy through fusion. Instead, gravity overwhelms the outward pressure generated by nuclear reactions, causing the core to collapse rapidly. This collapse triggers a catastrophic rebound, leading to a supernova explosion. The energy released in a supernova is staggering, briefly outshining an entire galaxy and releasing as much energy in a few weeks as the Sun will emit over its entire lifetime. Supernovae are classified into several types based on their characteristics and the mechanisms that trigger them. Type I supernovae occur in binary star systems where a white dwarf accretes material from a companion star, exceeding a critical mass and triggering a runaway fusion reaction that destroys the star. These explosions are incredibly consistent in their brightness, making them invaluable tools for measuring cosmic distances and probing the universe's expansion. Type II supernovae, on the other hand, result from the collapse of massive stars. As the iron core collapses, it releases shockwaves that propagate through the star's outer layers, causing them to explode outward in a titanic explosion. These supernovae are crucial for enriching the interstellar medium with heavy elements such as iron, nickel, and even gold. Elements that are essential for the formation of new stars, planets, and life. The impact of supernovae on cosmic evolution is profound. These explosions scatter elements forged in their cores across vast regions of space, enriching interstellar clouds with the raw materials needed for the formation of future generations of stars and planetary systems. The shockwaves from supernovae can trigger the collapse of nearby gas clouds, initiating the birth of new stars and continuing the cycle of stellar birth and death that shapes galaxies. Observing supernovae is both a historical and modern pursuit. Ancient civilizations recorded sudden appearances of new stars in the sky, unaware that these were distant supernovae. Today, advanced telescopes and observatories, such as the Hubble Space Telescope and ground-based surveys, monitor the universe for these explosive events. By studying the light emitted during and after a supernova, astronomers can glean insights into the processes that govern these cataclysmic explosions, from the physics of stellar collapse to the dynamics of shockwave propagation. Looking to the future, ongoing advancements in observational technology and theoretical modeling promise to deepen our understanding of supernovae. New generations of telescopes, such as the James Webb Space Telescope and the Vera C. Rubin Observatory, will provide unprecedented views of supernovae across different wavelengths of light, offering new insights into their diversity and underlying mechanisms. Chapter 3: Gamma-ray bursts, the universe's most powerful explosions. Gamma-ray bursts, GRBs, are the universe's most energetic and mysterious explosions, releasing more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. These cosmic cataclysms were first discovered serendipitously in the late 1960s by satellites designed to detect nuclear tests on Earth. Instead of terrestrial events, they detected intense bursts of gamma rays originating from deep space, baffling astronomers and prompting decades of research into their origins and implications. GRBs come in two primary types, classified by their duration and spectral properties: long-duration GRBs, lasting more than 2 seconds, and short-duration GRBs, lasting less than 2 seconds. Long GRBs are generally associated with the collapse of massive stars, specifically the cores of massive stars collapsing to form black holes. Short GRBs, on the other hand, are believed to result from the merger of compact objects such as neutron stars or a neutron star and a black hole. The precise mechanisms behind GRBs are still subject to active research and debate. One of the leading models for long GRBs is the collapsar model, where a massive star undergoes a supernova explosion, leaving behind a black hole surrounded by an accretion disk. The material falling into the black hole forms relativistic jets along its rotational axis, producing the intense burst of gamma rays observed from Earth. Short GRBs are theorized to occur when two compact objects, such as neutron stars, spiral toward each other and merge. The merger process generates powerful jets of gamma rays and gravitational waves, marking the cataclysmic union of two extremely dense stellar remnants. The energy released in a GRB is staggering, with some bursts emitting more energy in a few seconds than our Sun will emit in its entire lifetime. These bursts are not only luminous in gamma-ray wavelengths, but also often exhibit afterglows across the electromagnetic spectrum, from X-rays to radio waves. These afterglows provide valuable clues about the environment surrounding the burst, the composition of the ejected material, and the physics of the explosion itself. The study of GRBs has profound implications for astrophysics and cosmology. These events serve as probes of the early universe, as some GRBs are detected at cosmological distances, offering a glimpse into the conditions of the universe's infancy. GRBs also play a role in the formation and evolution of galaxies, potentially influencing the rate of star formation and the distribution of heavy elements. Observing GRBs is challenging due to their brief and unpredictable nature. Detecting and studying these events require dedicated space-based observatories equipped with sensitive instruments capable of capturing fleeting bursts of gamma rays and their subsequent afterglows. Missions like NASA's SWIFT satellite and the Fermi Gamma Ray Space Telescope have revolutionized our understanding of GRBs by providing continuous monitoring and rapid follow-up observations. The future of GRB research holds promise with upcoming missions and technological advancements. New generations of telescopes, such as the Advanced LIGO and Virgo gravitational wave detectors and future space-based observatories, will further enhance our ability to detect and study these cosmic explosions. These efforts will not only deepen our understanding of the physical processes driving GRBs, but also shed light on their role in shaping the universe's evolution and structure. Chapter 4: Black Hole Mergers, Cosmic Collisions and Gravitational Waves. Black hole mergers represent one of the most violent and energetic events in the universe. These cosmic collisions occur when two black holes spiral towards each other, merging into a single, more massive black hole and releasing immense amounts of energy in the form of gravitational waves. These events not only reshape our understanding of black holes and their dynamics, but also provide crucial insights into the fundamental nature of gravity and space-time. Black holes, the remnants of massive stars that have ended their lives in supernova explosions, are regions of space where gravity is so strong that nothing, not even light, can escape. They come in various sizes, from stellar mass black holes, which are a few times more massive than the Sun, to supermassive black holes, which reside at the centers of galaxies and have masses millions to billions of times that of the Sun. When two black holes form a binary system, they gradually lose energy through the emission of gravitational waves, causing them to spiral inward toward an inevitable collision. Gravitational waves, ripples in space-time predicted by Albert Einstein's theory of general relativity, were first directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. This groundbreaking discovery confirmed a century-old prediction and opened a new window into the universe, allowing us to observe cosmic events that are otherwise invisible through traditional electromagnetic observations. The first detected gravitational wave signal, named GW150914, came from the merger of two black holes about 1.3 billion light-years away, each roughly 30 times the mass of the Sun. The process leading up to a black hole merger is a ballet of immense forces and energies. As the black holes spiral closer, they emit gravitational waves with increasing frequency and amplitude. This phase, known as the inspiral, is followed by the merger, where the two black holes collide and coalesce into a single, distorted black hole that quickly settles into a stable form, emitting a final burst of gravitational waves called the ringdown. These gravitational waves carry away a significant portion of the system's energy, equivalent to several solar masses converted directly into gravitational radiation. Black hole mergers are not just spectacular in terms of energy release. They are also rich in information about the properties of black holes and the nature of gravity. By analyzing the gravitational wave signals from these events, scientists can measure the masses and spins of the merging black holes, test the predictions of general relativity in extreme conditions, and explore the environments in which these mergers occur. For instance, the spin orientations of the black holes can provide clues about their formation history, whether they formed together as a binary system or came together in a dense stellar environment such as a globular cluster. The study of black hole mergers has significant implications for our understanding of the universe. It offers a unique way to explore the population and distribution of black holes, shedding light on their formation and evolution. It also provides a natural laboratory for testing the limits of general relativity, possibly uncovering new physics beyond our current theories. Furthermore, the detection of gravitational waves from black hole mergers complements electromagnetic observations, creating a more comprehensive picture of the dynamic universe. Looking ahead, the field of gravitational wave astronomy is poised for rapid growth. Upgrades to existing detectors like LIGO and Virgo, along with the construction of new observatories such as the Kagra in Japan and the future Einstein telescope in Europe, promise to increase the sensitivity and frequency of detections. Space-based detectors like the Laser Interferometer Space Antenna, LISA, will further expand our observational capabilities, allowing us to detect gravitational waves from sources that are inaccessible to ground-based detectors, such as mergers of supermassive black holes and binary systems involving neutron stars and white dwarfs. Chapter 5. Neutron Star Collisions. Unleashing the Universia's Gold Mines. Neutron star collisions, also known as kilonovae, are among the most fascinating and powerful events in the cosmos. When these incredibly dense stellar remnants collide, they release a burst of gravitational waves and electromagnetic radiation, along with a wealth of heavy elements like gold and platinum. This chapter delves into the nature of neutron stars, the dynamics of their collisions, and the profound impact these events have on our understanding of the universe. Neutron stars are the remnants of massive stars that have exploded in supernovae. After the outer layers are ejected, the core collapses into a superdense object primarily composed of neutrons. These stars pack more mass than the Sun into a sphere only about 20 kilometers across, making them some of the densest objects in the universe. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars exhibit extreme magnetic fields and rapid rotation, often observed as pulsars emitting beams of radiation. When two neutron stars orbit each other in a binary system, they gradually spiral closer due to the emission of gravitational waves. This process can take millions or even billions of years, but it ends in a spectacular collision. The first direct detection of such an event, GW170817, occurred in 2017, marking a watershed moment in multi-messenger astronomy. This event was observed through both gravitational waves by the LIGO and Virgo detectors and electromagnetic signals by telescopes across the spectrum. The collision of neutron stars involves a complex interplay of extreme physics. As the stars spiral together, tidal forces deform them, and just before the merger, they eject a fraction of their mass into space. The collision itself releases a massive amount of energy, creating a short gamma-ray burst, GRB, followed by an afterglow of light that can be observed across multiple wavelengths. This afterglow, known as a kilonova, is powered by the radioactive decay of heavy elements formed in the collision. One of the most significant contributions of neutron star collisions to cosmic alchemy is the production of heavy elements. The intense environment of the collision enables rapid neutron capture, or the R process, which creates elements heavier than iron. Observations of GW 170817 provided direct evidence that these mergers are indeed sites of heavy element formation, solving a long-standing mystery about the origins of elements like gold, platinum, and uranium. The gravitational waves from neutron star mergers offer a wealth of information. They allow astronomers to measure the masses and radii of the neutron stars, providing insights into the state of matter under extreme pressure. This information is crucial for understanding the equation of state of neutron star matter, which describes how matter behaves at densities far beyond those found in atomic nuclei. These measurements also test the predictions of general relativity in the strong field regime, providing stringent tests of our understanding of gravity. The electromagnetic counterpart of a neutron star merger, the kilonova, offers additional clues. The light curves and spectra of kilonovae reveal the presence of heavy elements and the conditions in the ejected material. By comparing observations with theoretical models, astronomers can refine their understanding of the R process and the overall contribution of neutron star mergers to the galactic chemical enrichment. Neutron star mergers also have broader implications for astrophysics and cosmology. They serve as standard sirens for measuring cosmic distances, providing an independent method to determine the Hubble constant, which describes the rate of the universe's expansion. This can help resolve discrepancies between different measurements of the Hubble constant, one of the most pressing issues in cosmology today. The future of neutron star collision research is bright, with more detections expected as gravitational wave observatories improve in sensitivity. Upcoming facilities like the Einstein Telescope and the Cosmic Explorer will detect these events from greater distances, increasing the volume of the universe we can study. Additionally, space-based observatories like the Laser Interferometer Space Antenna, LISA, will complement ground-based detectors by observing gravitational waves from different types of sources, including neutron star mergers in different environments. Chapter 6: Galactic Collisions, the Dance of Destruction and Creation. Galactic collisions are among the most awe-inspiring and dynamic events in the universe, involving the interaction and merging of entire galaxies over timescales of hundreds of millions to billions of years. These colossal encounters dramatically reshape galaxies, trigger intense bursts of star formation, and influence the growth of supermassive black holes at their centers. In this chapter, we explore the mechanisms, consequences, and significance of galactic collisions in the cosmic landscape. Galaxies are vast assemblies of stars, gas, dust, and dark matter, bound together by gravity. Our Milky Way galaxy, for instance, contains over 100 billion stars, along with an even greater amount of dark matter. Galaxies do not exist in isolation. They are part of larger structures called galaxy clusters, where interactions and collisions are relatively common over cosmic timescales. When two galaxies approach each other, their mutual gravitational attraction can lead to a slow-motion collision, a cosmic dance that unfolds over millions of years. The process of galactic collision begins with a close encounter, during which the gravitational forces of the galaxies start to interact. These forces can distort the shapes of the galaxies, pulling out long tidal tails of stars and gas. As the galaxies draw closer, their mutual gravitational pull grows stronger, leading to more pronounced distortions and mixing of their components. Eventually, the galaxies merge, forming a single, larger galaxy. This merger process can trigger several significant astrophysical phenomena. One of the most noticeable effects of a galactic collision is a burst of star formation, often referred to as a starburst. As the galaxies merge, their gas clouds collide and compress, creating conditions ripe for the rapid formation of new stars. These starbursts can be so intense that they outshine the combined light of the original galaxies, contributing to the growth and evolution of the stellar populations within the resulting galaxy. Starburst regions are often visible as bright, blue patches, indicating the presence of hot, young stars. Another critical consequence of galactic collisions is the fueling of supermassive black holes at the centers of galaxies. These black holes, which can have masses millions to billions of times that of the Sun, lie dormant for much of their lives. However, during a galactic collision, gas and dust can be funneled into the central regions, providing a fresh supply of material for the black hole to consume. This accretion process ignites the black hole, causing it to emit vast amounts of radiation and creating an active galactic nucleus, AGN. AGNs are some of the brightest objects in the universe, capable of outshining their host galaxies and providing valuable insights into the physics of black holes and galaxy evolution. Galactic collisions also play a vital role in the morphological transformation of galaxies. Spiral galaxies, like the Milky Way, can be transformed into elliptical galaxies through the merging process. The violent interactions during the merger randomize the orbits of stars, leading to a more spheroidal distribution characteristic of elliptical galaxies. These transformations are essential for understanding the diversity of galaxy shapes and the evolutionary pathways that lead to the variety of galaxies observed in the universe today. Observing galactic collisions provides astronomers with crucial data on the dynamics of galaxies and the underlying distribution of dark matter. Since dark matter does not interact with electromagnetic radiation, its presence can only be inferred through its gravitational effects on visible matter. During a galactic collision, the distribution of dark matter can be mapped by studying the motions of stars and gas, offering vital clues about its nature and distribution. Galactic collisions are also a key component in the hierarchical model of galaxy formation and evolution, which posits that large galaxies form through the merging of smaller ones. This model is supported by observations of distant, early galaxies that appear smaller and less structured compared to nearby, mature galaxies. By studying collisions at various stages of cosmic history, astronomers can piece together the timeline of galaxy assembly and the growth of cosmic structures. The Milky Way itself is not immune to galactic collisions. In fact, it is on a collision course with the nearby Andromeda galaxy. This monumental event is expected to occur in about 4 billion years, leading to the formation of a new galaxy often referred to as Milkomeda or Milkdromeda. While the collision will dramatically reshape both galaxies, the vast distances between individual stars mean that direct stellar collisions will be rare, although the night sky will be spectacularly altered. Chapter 7: Cosmic Rays, the high-energy particles from deep space. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, bombarding the Earth from all directions. These particles, which include protons, electrons, and atomic nuclei, originate from a variety of sources, both within our galaxy and beyond. The study of cosmic rays provides valuable insights into some of the most energetic and violent processes in the universe, as well as their impact on Earth and the solar system. Cosmic rays were first discovered in the early 20th century when scientists noticed that radiation levels measured at high altitudes were significantly higher than those at sea level. This led to the realization that there were energetic particles originating from outer space. Further research revealed that cosmic rays come from various sources, including the Sun, supernovae, neutron stars, black holes, and even more distant and energetic phenomena such as active galactic nuclei and gamma-ray bursts. The vast majority of cosmic rays are protons, but they also include heavier nuclei and a small fraction of electrons and positrons. When these high-energy particles strike the Earth's atmosphere, they interact with atmospheric nuclei, producing showers of secondary particles. These secondary particles, including muons and neutrinos, cascade down to the Earth's surface, where they can be detected by ground-based instruments. The energy of cosmic rays spans an enormous range, from relatively low-energy particles produced by the Sun to ultra-high-energy cosmic rays with energies exceeding 10 to the power of 20 electron volts, far higher than any particle accelerator on Earth can achieve. These ultra-high-energy cosmic rays are particularly intriguing because their origin remains one of the biggest mysteries in astrophysics. They are believed to be accelerated by the most powerful astrophysical processes, such as the shock waves from supernova explosions or the jets emanating from supermassive black holes. Supernovae are one of the primary sources of cosmic rays. When a massive star explodes, it creates shock waves that can accelerate particles to extremely high energies. These particles then propagate through space, gradually losing energy as they interact with interstellar matter and magnetic fields. The interaction of cosmic rays with the galactic magnetic field causes them to spiral and change direction, making it challenging to trace them back to their original sources. Another significant source of cosmic rays is the sun's solar cosmic rays are primarily produced during solar flares and coronal mass ejections, where the sun's magnetic field accelerates particles to high energies. These solar cosmic rays can have a significant impact on the Earth's magnetosphere, leading to geomagnetic storms that can disrupt communication systems, satellites, and power grids. They also pose a radiation hazard to astronauts and high-altitude flights. Cosmic rays have a profound impact on the Earth's atmosphere and climate. When cosmic rays interact with the atmosphere, they ionize molecules, leading to the formation of clouds. Some theories suggest that variations in cosmic ray intensity, influenced by solar activity and the Earth's magnetic field, could affect cloud cover and, consequently, the Earth's climate. However, the extent of this influence remains a topic of ongoing research and debate. The study of cosmic rays also provides insights into fundamental physics. For instance, cosmic ray detectors have discovered particles with energies far exceeding those achievable by human-made accelerators, offering a natural laboratory for studying high-energy particle interactions. Additionally, the detection of antimatter particles, such as positrons and antiprotons, in cosmic rays raises intriguing questions about the nature of dark matter and the asymmetry between matter and antimatter in the universe. Detecting and studying cosmic rays requires sophisticated instruments. Ground-based observatories like the Pierre Auger Observatory and space-based detectors, such as the Alpha Magnetic Spectrometer on the International Space Station, are designed to capture and analyze cosmic rays. These instruments measure the energy, composition, and arrival direction of cosmic rays, providing valuable data for understanding their origins and propagation. Future research in cosmic ray physics aims to unravel the mysteries of their sources and acceleration mechanisms. Upcoming observatories and missions, such as the Cherenkov Telescope Array and the Extreme Universe Space Observatory, will enhance our ability to detect and analyze high-energy cosmic rays. Advances in technology and data analysis will also improve our understanding of the relationship between cosmic rays and other astrophysical phenomena, such as gamma-ray bursts and active galactic nuclei. Chapter 8: The Great Attractor, Cosmic Enigma of Gravitational Anomalies. The Great Attractor is one of the most intriguing and perplexing features in the universe, an immense gravitational anomaly that exerts a significant pull on the Milky Way and many other galaxies within our local cosmic neighborhood. Discovered in the 1980s, the Great Attractor's precise nature and composition remain shrouded in mystery, compelling astronomers to delve deeper into the dynamics of large-scale cosmic structures and the forces that govern them. The concept of the Great Attractor emerged from studies of the cosmic microwave background radiation, the remnant heat from the Big Bang, and the motion of galaxies. Scientists observed that galaxies in our local supercluster, including the Milky Way, were not merely expanding away from each other due to the universe's overall expansion. Instead, they were moving towards a specific region in space at extraordinary speeds. This motion suggested the presence of a massive, unseen gravitational source, later dubbed the Great Attractor. Located roughly 150 to 250 million light-years away in the direction of the constellations Centaurus and Norma, the Great Attractor resides in a region of the sky heavily obscured by the plane of the Milky Way, making it challenging to observe directly. This area, known as the Zone of Avoidance, contains a dense concentration of gas, dust, and stars, which block our view of the distant universe. Despite these observational hurdles, astronomers have employed various techniques, including X-ray and infrared surveys, to peer through the obscuration and investigate the nature of the Great Attractor. One of the leading hypotheses is that the Great Attractor is a massive supercluster of galaxies, or even a complex network of several superclusters, whose combined gravitational pull influences the motion of galaxies over a vast region of space. This structure, known as the Laniakea supercluster, encompasses the Virgo supercluster, the Hydra Centaurus supercluster, and other galaxy groups, forming an immense gravitational basin. Within this basin, galaxies flow towards a central point, much like water draining into a whirlpool. The study of the Great Attractor provides crucial insights into the distribution of dark matter, which constitutes about 85% of the total mass of the universe but does not emit or absorb light. Dark matter's gravitational influence is essential for explaining the observed motions of galaxies and the formation of large-scale structures. By mapping the motions of galaxies and their velocities, astronomers can infer the distribution and density of dark matter in the region surrounding the Great Attractor. Despite its name, the Great Attractor is not a single point, but rather a diffuse region with a complex gravitational field. It is part of an even larger structure known as the Shapley supercluster, one of the most massive superclusters in the nearby universe, located beyond the Great Attractor. The Shapley supercluster exerts its own significant gravitational influence, suggesting that the motion of galaxies in our local area is the result of a combination of forces from multiple large-scale structures. The discovery and study of the Great Attractor have profound implications for our understanding of cosmology and the large-scale structure of the universe. It challenges the notion of a homogeneous and isotropic universe, suggesting that large-scale anisotropies and inhomogeneities play a crucial role in the cosmic web's dynamics. These findings also highlight the importance of gravitational interactions in shaping the universe's evolution over billions of years. Ongoing research into the Great Attractor and its surrounding regions continues to reveal new and surprising aspects of the universe's structure. The development of more advanced observational tools, such as next-generation X-ray and infrared telescopes, will enable astronomers to probe deeper into the zone of avoidance and obtain clearer views of the hidden cosmic landscape. Additionally, future surveys and simulations will help refine our models of large-scale cosmic flows and the distribution of dark matter. Chapter 9. Magnetar Outbursts, the universe's most powerful magnetic explosions. Magnetars are a rare and extraordinary type of neutron star, distinguished by their incredibly powerful magnetic fields. These magnetic fields, a quadrillion times stronger than Earth's, make magnetars the most magnetic objects known in the universe. When these fields undergo sudden, catastrophic reconfigurations, they release enormous amounts of energy in the form of gamma-ray and X-ray bursts, creating some of the most intense explosions observed in the cosmos. This chapter explores the origin, nature, and impact of magnetar outbursts, shedding light on these mysterious and violent celestial phenomena. Neutron stars are the remnants of massive stars that have ended their lives in supernova explosions. While most neutron stars are detected as pulsars, emitting regular pulses of radiation as they spin, a small fraction are born with or acquire extremely strong magnetic fields. These magnetars, numbering only around 30 known examples, exhibit behaviors that set them apart from other neutron stars. The magnetic field of a magnetar can be so intense that it deforms the neutron star's crust and accelerates particles to nearly the speed of light. Magnetar outbursts occur when the intense magnetic field undergoes a sudden rearrangement, often due to magnetic stress building up over time. This process is akin to the Earth's magnetic field experiencing a violent shift, but on a vastly more energetic scale. The reconfiguration releases a colossal amount of energy, which heats the neutron star's crust and generates powerful flares of high-energy radiation. These outbursts can last from a fraction of a second to several minutes and are typically followed by a period of lower level, but still significant, X-ray emissions. One of the most dramatic examples of a magnetar outburst was observed on December 27, 2004, when SGR 1806-20, a magnetar located about 50,000 light-years away in the constellation Sagittarius, produced a giant flare. This flare released more energy in a fraction of a second than the Sun emits in 100,000 years. The initial gamma-ray burst was so intense that it momentarily altered the Earth's ionosphere, affecting radio transmissions and demonstrating the profound impact these distant events can have on our planet. The energy released during a magnetar outburst primarily comes from the magnetic field itself, a phenomenon that distinguishes magnetar flares from other high-energy astrophysical events such as supernovae or gamma-ray bursts, which are powered by gravitational energy. The magnetic energy is stored in the magnetar's magnetic field and is released when the field lines twist, snap, and reconnect, similar to how solar flares are produced by the Sun's magnetic field but on a much larger and more violent scale. The extreme conditions surrounding magnetar outbursts provide a natural laboratory for studying physical processes that cannot be replicated on Earth. For instance, The magnetic fields involved are so strong that they affect the vacuum of space itself, causing it to behave as a birefringent medium where light of different polarizations travels at different speeds. This effect, known as vacuum birefringence, is predicted by quantum electrodynamics, QED, and offers a way to test fundamental physical theories under extreme conditions. Magnetar outbursts also offer insights into the internal structure of neutron stars. The energy released during an outburst can trigger seismic waves within the neutron star's crust, akin to starquakes. These starquakes provide information about the star's density, composition, and internal magnetic field structure, helping scientists refine their models of neutron star interiors. Additionally, studying the timing and energy spectra of the flares helps astronomers understand the mechanisms behind magnetic field reconfigurations and particle acceleration. The study of magnetars is still a relatively young field, with many unanswered questions about their formation, evolution, and ultimate fate. Some theories suggest that magnetars are born from the most massive stars, which explode as hypernovae, leaving behind a rapidly rotating, highly magnetized neutron star. Alternatively, magnetars might form from the merger of neutron stars or from binary systems where accretion processes amplify the magnetic field. The diversity of possible origins and the extreme environments they inhabit make magnetars a key focus of high-energy astrophysics. Future observations and theoretical developments will continue to advance our understanding of magnetars and their outbursts. Upcoming space telescopes like the Advanced Telescope for High-Energy Astrophysics, Athena, and ground-based observatories like the Cherenkov Telescope Array, CTA, will provide more detailed observations of magnetar flares across different wavelengths. Additionally, advancements in computational astrophysics will enable more sophisticated models of magnetar magnetic field dynamics and crustal physics. Chapter 10: Galactic Winds, the Universe's Violent Cosmic Breezes. Galactic winds are powerful streams of charged particles and gas that flow out of galaxies, driven by intense astrophysical processes such as supernova explosions, star formation, and active galactic nuclei, AGN. These winds play a crucial role in the evolution of galaxies, regulating star formation, redistributing elements, and influencing the intergalactic medium. This chapter explores the mechanisms behind galactic winds, their impact on galaxies and the broader cosmos, and their significance in our understanding of galactic and cosmic evolution. The primary drivers of galactic winds are stellar feedback mechanisms and AGN activity. Stellar feedback refers to the energy and momentum input from massive stars through processes such as supernovae, stellar winds, and radiation pressure. When massive stars reach the end of their lives, they explode as supernovae, injecting enormous amounts of energy into the surrounding interstellar medium, ISM. This energy heats the gas, causing it to expand and flow out of the galaxy in a process known as a superwind. Superwinds can carry significant amounts of gas and dust out of the galaxy, creating large-scale outflows that extend thousands of light-years into intergalactic space. These winds are observed in many starburst galaxies, where intense periods of star formation lead to numerous supernovae, driving powerful outflows. The interaction of these winds with the surrounding ISM can trigger the formation of new stars by compressing gas clouds, or it can suppress star formation by removing gas from the galaxy, a process known as feedback regulation. Active galactic nuclei, AGN, powered by supermassive black holes at the centers of galaxies, are another major source of galactic winds. As matter accretes onto the black hole, it releases vast amounts of energy in the form of radiation, jets, and winds. The radiation pressure and mechanical forces from these outflows can drive gas out of the galaxy, creating AGN-driven winds. These winds can be extremely powerful, reaching velocities of thousands of kilometers per second, and can have profound effects on the host galaxy and its environment. One of the critical roles of galactic winds is the regulation of star formation. By expelling gas from galaxies, winds can deplete the raw material needed for star formation, thereby quenching further star formation activity. This feedback mechanism is essential for explaining the observed properties of galaxies, such as the correlation between the mass of the central supermassive black hole and the velocity dispersion of the galaxy's stars, known as the M-sigma relation. Without such feedback processes, galaxies would form stars too efficiently, leading to an overabundance of massive, star-rich galaxies. Galactic winds also contribute to the chemical enrichment of the intergalactic medium, IgM. As winds expel gas from galaxies, they carry with them elements produced by stellar nucleosynthesis, such as carbon, oxygen, and iron. These metals enrich the IgM, influencing the chemical composition of future generations of stars and galaxies. Observations of the IgM, through absorption lines in the spectra of distant quasars, reveal the widespread presence of these metals, indicating that galactic winds have played a significant role in distributing elements across the cosmos. The interaction between galactic winds and the IgM can also lead to the formation of large-scale structures. Winds can compress and shock heat the IgM, creating regions of high density and temperature that can collapse to form new galaxies and clusters. This process is an essential component of the hierarchical model of structure formation, where small structures merge and grow to form larger ones over cosmic time. Observations of galactic winds come from various wavelengths, each providing unique insights into the properties and impact of these outflows. X-ray observations, for example, can detect the hot gas in superwinds and AGN-driven winds, revealing the temperature, density, and velocity of the outflowing material. Optical and ultraviolet spectroscopy can trace the ionized gas, providing information about the chemical composition and kinematics of the winds. Radio observations can detect the cold molecular gas, which is crucial for understanding the amount of gas being removed from galaxies and its impact on star formation. Galactic winds are also an essential factor in the evolution of galaxy clusters. In these dense environments, interactions between galaxies and the intracluster medium, ICM, can enhance wind activity, leading to more efficient removal of gas and regulation of star formation. The combined effect of winds from multiple galaxies can enrich the ICM with metals, influencing the thermal and chemical properties of the cluster. Theoretical models and simulations play a vital role in studying galactic winds. These models help to understand the complex interplay between different feedback mechanisms, the propagation of winds through the ISM and IgM, and their impact on galaxy evolution. Advances in computational power and techniques have enabled more detailed and realistic simulations, providing valuable insights into the physics of galactic winds and their role in the cosmic ecosystem. Chapter 11. The Big Rip, the Ultimate Fate of the Universe. The Big Rip is one of the most dramatic and terrifying theoretical scenarios for the ultimate fate of the universe. According to this hypothesis, the accelerating expansion of the universe, driven by dark energy, will continue to increase until it eventually tears apart all structures in the cosmos, from galaxies and stars to atoms and subatomic particles. This chapter delves into the concept of the Big Rip, exploring the underlying physics, the timeline of events leading to this cataclysmic end, and the current scientific understanding of dark energy. The notion of the Big Rip arises from observations that the universe's expansion is not slowing down, as once thought, but accelerating. This acceleration is attributed to dark energy, a mysterious and poorly understood form of energy that permeates all of space. Dark energy constitutes about 68% of the total energy density of the universe, with dark matter making up about 27% and ordinary matter only about 5%. The discovery of the accelerating expansion was made in the late 1990s through observations of distant type I supernovae. These observations revealed that galaxies are receding from us at an ever-increasing rate, suggesting that some force is driving this acceleration. The exact nature of dark energy remains one of the most significant mysteries in modern cosmology. It could be a property of space itself, represented by a cosmological constant, or it could be a dynamic field, often referred to as quintessence. In the Big Rip scenario, the density of dark energy increases over time, leading to an ever faster expansion of the universe. This concept hinges on the equation of state parameter \W \, which describes the relationship between the pressure and density of dark energy. If \W is less than -1, the dark energy is referred to as phantom energy, and it predicts a future in which the universe's expansion rate accelerates without bound. As the expansion accelerates, the gravitational forces that hold galaxies, stars, and even atoms together are eventually overcome by the repulsive force of dark energy. The timeline of events leading to the Big Rip, while speculative, can be outlined as follows. 1. Billions of years before the Big Rip, the universe continues to expand at an accelerating rate. Galaxies recede from each other, and intergalactic space stretches, leading to increasing isolation of galactic clusters. 2. Hundreds of millions of years before the Big Rip, gravitationally bound structures such as galaxy clusters and individual galaxies begin to be torn apart as the expansion rate surpasses the binding gravitational forces. 3. Millions of years before the Big Rip, star systems within galaxies, including our solar system, are disrupted. Stars are no longer gravitationally bound to their galaxies and start drifting apart. 4. Days to hours before the Big Rip, planets are ripped away from their parent stars as the tidal forces from the accelerating expansion become stronger than the gravitational forces holding them in orbit. 5. Minutes before the Big Rip, stars themselves are torn apart. The expansion becomes so extreme that it overwhelms the nuclear forces holding atomic nuclei together. 6. Fractions of a second before the Big Rip, atoms and subatomic particles are shredded. The fabric of space-time itself is ripped apart, leading to a singularity or a complete dissolution of all matter. The mathematical foundation for the Big Rip is rooted in cosmological equations that describe the dynamics of dark energy. If dark energy density increases without bound, it leads to a finite time in the future when the scale factor of the universe becomes infinite, marking the end of time as we understand it. However, it is essential to note that the Big Rip is a theoretical construct and remains speculative. Current observations do not provide definitive evidence for phantom energy or an equation of state parameter \W significantly less than -1. Other models of dark energy, such as those involving a cosmological constant with \W equals -1 or quintessence with \W varying over time but typically greater than -1, do not predict a Big Rip. Furthermore, future observations, particularly those from upcoming space missions and advanced ground-based telescopes, will refine our understanding of dark energy's properties. Projects such as the Euclid mission, the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory are expected to provide more precise measurements of cosmic expansion and the behavior of dark energy over time. Chapter 12. Gamma ray bursts, the universe's most explosive events. Gamma ray bursts, GRBs, are the most luminous and energetic explosions observed in the universe, capable of releasing more energy in a few seconds than the sun will emit in its entire 10 billion-year lifetime. These cataclysmic events, detected primarily through their gamma ray emissions, occur when massive stars collapse or when neutron stars merge. This chapter delves into the nature, origins, and implications of GRBs, exploring how they provide a window into the most extreme and violent processes in the cosmos. Gamma ray bursts were first discovered in the late 1960s by the Vela satellites, launched by the United States to monitor nuclear tests. Instead of detecting terrestrial explosions, the satellites recorded intense bursts of gamma rays from deep space, marking the beginning of GRB astronomy. These bursts are classified into two main types based on their duration: long-duration GRBs, lasting more than 2 seconds, and short-duration GRBs, lasting less than 2 seconds. Despite their brevity, both types of GRBs emit tremendous amounts of energy. Long-duration GRBs are typically associated with the deaths of massive stars in distant galaxies. When such a star exhausts its nuclear fuel, its core collapses into a black hole or neutron star, while the outer layers are expelled in a supernova explosion. During this collapse, if the core's spin and magnetic field conditions are right, a jet of highly relativistic particles is launched along the star's rotational axis. These jets break through the star's surface and, if pointed towards Earth, are observed as a GRB. The associated supernova, known as a hypernova, is extraordinarily energetic and further contributes to the light show. Short-duration GRBs, on the other hand, are believed to originate from the mergers of compact objects, such as neutron stars or a neutron star and a black hole. These mergers result in the formation of a black hole and the ejection of ultra-fast jets of particles, producing a GRB. The detection of gravitational waves from such mergers by observatories like LIGO and Virgo coinciding with the observation of a short GRB, has confirmed this origin. These mergers also produce heavy elements, such as gold and platinum, in a process known as kilonova, enriching the universe with these precious materials. The study of GRBs involves a variety of observational techniques and instruments. Space-based observatories like the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope are crucial for detecting the initial burst of gamma rays and quickly alerting astronomers to its location. These alerts enable follow-up observations across the electromagnetic spectrum, from X-rays and optical light to radio waves, providing a comprehensive picture of the event and its aftermath. The afterglow of a GRB, the fading emission following the initial burst, is particularly important for understanding the underlying mechanisms. The afterglow is produced by the interaction of the GRB jet with the surrounding interstellar medium, causing shock waves that emit radiation at various wavelengths. By studying the afterglow, astronomers can infer the properties of the jet, such as its energy, composition, and the environment around the GRB progenitor. GRBs are not only remarkable for their energy, but also for their cosmological significance. Because they are visible across vast distances, GRBs serve as beacons that illuminate the far reaches of the universe. They provide valuable information about the early universe, star formation rates, and the evolution of galaxies. Some GRBs have been detected from epochs when the universe was less than 1 billion years old, offering insights into the conditions and processes that prevailed at that time. One of the most intriguing aspects of GRBs is their potential role in the evolution of life. The immense energy released in a GRB can have devastating effects on any nearby planets. A GRB occurring within a few thousand light-years of Earth could strip away the planet's ozone layer, exposing life to harmful ultraviolet radiation from the sun. Some researchers have speculated that past mass extinction events on Earth could have been triggered by nearby GRBs. However, the likelihood of such an event happening in the near future is extremely low, given the vast distances between potential GRB progenitors and our solar system. The theoretical understanding of GRBs has advanced significantly over the past few decades, with detailed models explaining the physical processes behind their formation and emission. These models involve complex relativistic hydrodynamics, particle acceleration, and radiation mechanisms. The interaction between theory and observation has been crucial, with each new GRB providing data that refine our models and improve our understanding of these extraordinary events. Future advancements in GRB research will come from both observational and theoretical fronts. Upcoming space missions, such as the Space Variable Objects Monitor (SVOM) and the Transient High Energy Sky and Early Universe Surveyor (THESIUS), will enhance our ability to detect and study GRBs. These missions will provide more precise localization, better timing resolution, and broader spectral coverage, allowing for more detailed studies of GRB physics and their environments. Additionally, advancements in multi-messenger astronomy, combining gravitational waves and electromagnetic observations, will continue to provide new insights into the origins and nature of short-duration GRBs.